This is the first time I've actually used that. So Avi is in Berkeley, California for the breakthrough discuss meeting. So I'm doing my best to represent him. And the theme of today's luncheon is that it is still possible to have an intellectual discussion that is not about M87. But I thought you might enjoy a picture from some of your colleagues. I believe that's in Washington Airport. But that's all we're going to have about M87. So the speaker lineup is really very interesting as it customarily is. So we'll hear first from John Lewis, who's one of our graduate students on CO depletion in California molecular cloud. And then we'll hear from our Sackville lecturer, Ken Freeman from Australia, from the Australian National University, Mark trapping and the Hercules moving group. And then Lisa Randall, who's just fresh from having given the ITC colloquium. We'll talk about rock and roll solutions to the Hubble tension. And then we'll hear from Vikram Ravi, also at the CFA, nearby nuclear radio transients. So John, feel free to take down M87.
All right, well, let's just get rid of M87 here. Yes. M87 is old news. I'm waiting for SAD J-star, which apparently I was duped into thinking that a simulation of it was a unreleased image. So I had to redact a tweet I sent out, which is never fun. All right. All right. So can everyone hear me all the way in the back? All right. Cool. Awesome. That's so I sit back there sometimes, and sometimes you say no, then the person says, "Great, let's go," and so it's good. So I'm John Lewis. I'm a something-year graduate student working with Charlie Latta here at the CFA, and we are generally interested in understanding the structure and composition of giant molecular clouds and how we can measure their masses, their star formation rates, and their sort of generic properties. And so most of the mass in giant molecular clouds, the sites of star formation in our galaxy, is molecular hydrogen. And so molecular hydrogen is extremely abundant, but the problem is that at the temperatures that are typical of giant molecular clouds, which is about 10 Kelvin, the hydrogen doesn't have any transitions that are visible. It's a symmetric dipole molecule, so the lowest temperature transitions are still in the hundreds of Kelvin to thousands of Kelvin range. And so we need something else to trace it. Historically, molecular hydrogen has been traced by looking either at visual extinction and comparing it to hydrogen absorption along the line of sight to stars, or in the 1970s, it was carbon monoxide was first detected by Bob Wilson of CMB fame. And carbon monoxide is the second most abundant molecule in the universe, being the direct product of stellar fusion. And so anytime a star explodes, it's going to throw out carbon and oxygen into the surrounding environment. The nice thing about dust extinction, though, is that it's a simple measurement. It doesn't depend on any of the line of sight properties except for how much molecular hydrogen there is and the gas to dust ratio, which does change. And in particular, it changes with cosmic time. And so we have two different methods that we can use to probe the molecular hydrogen. There's others, but I won't get into them. And these two proxies have their own perks. And so CO is abundant. It has bright emission lines that can be observed in distant galaxies across many redshifts. ALMA is doing extremely wonderful work with this. You also get kinematic information. So if you don't trust your your CO line, the brightness, you can get an estimate of the mass from a virial analysis. And it's extragalactically accessible. Dust extinction, however, you're limited to the galaxy. You can't measure, in Andromeda you can measure dust extinction, but in general you can't measure dust extinction in distant galaxies. But the nice thing is that it's very simple. It has we have a very accurate and precise knowledge of how it relates to the molecular hydrogen. And In Alyssa Goodman's work back in 2003, she found that dust extinction is the best tracer for molecular hydrogen in the galaxy. And so we want to find a way to combine these two to look at to get a good idea and a good understanding of the relationship between carbon monoxide and dust extinction. In general, both of these are converted to hydrogen with a simple linear conversion. In the case of carbon monoxide, it's called XCO or alpha CO for extragalactic folks, and dust extinction is just the dust to gas conversion factor. And so their relationship, you would think, should be simply linear. An excellent place to study this relationship is in the California molecular cloud. It is one of the largest and most massive molecular clouds in the local galaxy. It rivals Orion, which is a beast of star formation for its mass. It has over 100,000 solar masses of material in it. It is 60 parsecs long from the tip at the bottom all the way up to what Charlie calls the claw. At first I didn't get it, then I realized this is New England. And so, yes. And so this map here was from 2009 when the cloud was first discovered. It was found that it had more stars in front of it than it should to be at the distance they thought it was, and we realized it was a new molecular cloud. And so this was the state of the art in 2009. Extinction based on 2 mass, you can get down to about AV of 6 to 10 in this, or an a K-band extinction of 6 to 10 for this cloud. And you can see stuff on the scale of about an arc minute or so. We can improve this with Herschel data. And so Herschel observed this cloud. The Herschel is basically everything in gray there that you see. And that doubles your resolution and it increases the depth you can go by an order of magnitude. So instead of being limited to depths of about 6 magnitudes of extinction in the K-band, you can get down all the way down to 60. You can get further down. We also completed a survey with the SMT, and I'm not going to mention its interesting association because it's barred today. But we completed a survey of CO, 3 isotopic logs of CO in the California molecular cloud. And everywhere that we had extinction above 3 magnitudes in the V band. And so we observed the region on the far left to you guys is, we call it Look H alpha, named so because of the star there that's illuminating a nebula that's just proud of the filament. And you also observed lens 1478 and the west portion, the portion that we just call west. Look H alpha was discussed in Kong 2015 using the 2 mass maps and our CO data, and so we improve on this by being able to go an order of magnitude deeper into the cloud, and also looking at nearly 3 times as much area as them. This one little region, Cal X, was written up in a paper by Nia Amara, where she looked at the cores and star formation in this cloud. One of the very nice things about California is that as you go across the cloud, in Look H alpha, you have a large amount of star formation. L1478, you have very little. And in the west, you have even less star formation. In the west, you only have 2 protostars total, and they're all in there in Cal X. And so this is the data. It's plotted. This is WCO, which is the integrated intensity of the CO. We observed 3 lines, 12CO, the rare isotopic log 13CO, and the even rarer C18O. The white contours are just there to show the structure, and you can see that the 12CO at the top doesn't really match a lot of the structure that you see in Herschel, whereas in 13CO, you can easily see things like the X-shaped region there. You can see lens 1478, which doesn't even really show up too well in 12CO. And in C18O, we only observed a portion of the cloud, and so this corresponds to the middle of the L1478 region. And so we can get a qualitative idea that the 12CO doesn't do such a good job, but that's because it saturates, of course, it's optically thick. And the 13CO, and C18O seem to track the AV pretty well. But if there's a linear relationship with them, we expect to be able to plot WCO against AV and get a single line. There's your line. It's in red. The data is in black. And so clearly there's no single relationship on this scale between WCO and AV. The benefit that we have, though, is that we also have temperature. And so we can disentangle some of what's going on in here. So when we plot the Herschel dust temperatures over it, we see a linear relationship for the hot gas. It's not correlated with the dust temperature, but it at least shows that if you select the hot dust, the stuff that's going to be really bright, you're going to be able to, you can derive an X factor for that. So if you're looking at hot gas, you can sort of assume that, you know what, maybe we have an X factor. That derives from the fact that the 12CO is proportional to the excitation temperature in the cloud. But in the cold, you have no relationship. That's flat. You have a constant amount of CO for a given AV. This is sort of expected in 12CO. You get optically thick, and you no longer see beyond a certain depth. And so you're only seeing so much material. And so we say, let's go to our rare isotopic logs that are not optically thick. Still, no line. In fact, so this one has 3 lines. That's great, but that's not helpful. You still don't have a single X factor. Still in the hot gas, you can sort of derive one. So this is still just the intensity. We want to understand maybe what's the abundance of CO doing. And so we can plot the column density instead. The color is still the dust temperature, just a slightly different color, somewhat different color scheme, much better than jet. And we see that the column density of CO, which you can think of as the abundance, stays flat. The column density stays flat, and so that implies that the CO isn't just hidden; it's actually being depleted from what we can see. Depletion would predict that if you measure the depletion, which is the ratio of the cloud abundance to the ISM abundance, that it should go down with temperature, because as the average line of sight temperature in the cloud goes up, you can liberate more CO from the grains, and you get so you'll be able to actually see your actual gas phase abundance will be higher. This is what Charlie Latta and Kramer did in 1999, and so we see that exact signature in California. And so as you go higher in dust temperature, your depletion goes down to 1. This isn't like fake. That's just actual. It's actually 1. That's why you see it varies around 1. It's just above 1 down here. And so in the hot gas, where the CO is completely desorbed from the grains, it's completely desorbed from the grains. You have no depletion, and as you go below the temperature at which CO will deplete onto grains, which is 17 Kelvin, you see your depletion increases. And so this is the first time we've been able to make this type of study in such detail, and in such depth, and on such a large scale. This is due to the fact that we have Herschel, and so we're no longer limited by the depth of our extinction maps. We show that a single X factor is completely unusable for looking at CO on small scales, and that depletion cannot be ignored in studies of WCO versus AV. And thank you. You can get them reliably from the dust, and so the dust along the line of sight basically just tracks the molecular hydrogen. This is, I think, mostly an empirical fact. I don't know the theoretical backing to that, but empirically we see that that when you measure extinction and you compare it to the hydrogen column density derived from actual absorption profiles of molecular hydrogen, they track very well. In other galaxies, what you'd have to do is you'd have to actually understand how much of the material is depleted in a molecular cloud. And that's something that we can do with this data set. We can understand what fraction of the cloud is depleted and thus CO dark.
Have you thought about extending this to different clouds with more active star formation, or more into the environment?
Yeah, so that's part of the reason why we chose California, is that we can actually do that experiment in a single cloud. And so you have high star formation and sort of like hotter gas in Look H alpha, and in the further two sections you have one with a lot of dense gas, one with low dense gas, both at low star formation, and so you can make that comparison. And we see differences in them, and it shows up in structure on the plot of WCO versus AV. But yes, also we want to extend this sort of analysis to basically as much of the galaxy as we can. Yeah.
Sort of self-advertisement alert.
Yeah.
We're building a satellite that will map the CO ice across the whole galaxy. So it'd be interesting to compare the measured ice column densities against the CO gas column densities. We'll get it throughout the Milky Way.
Yeah, that would be excellent. So right now that's sort of like pinpoints that they have, and they don't go up to these extinctions, and so that would be excellent.
To your question, Charles, separately we're building an instrument for Sophia that, among other things, will measure HD.
Oh, nice.
Which is a surrogate for H2, with the advantage that HD does have a dipole moment,
Yeah.
and it has a lower first excited state.
Right.
So if the gas temperature isn't too cold, we should be able to get an estimate of the H2 column density directly from the HD, modulo that small uncertainty of the D-day ratio.
Yeah. No, that's really nice. And so Nia.
Although you had variation in the X factor, it looks like it hovered around what we considered standard galactic value. Was that a surprise, or was that expected?
So it's kind of. So it's kind of what you'd expect, because the average galactic value is just an average for all of the clouds, and so if you fit a line to this data that goes through 0, it actually gives you the Milky Way CO value, pretty much exactly, which is cool. It's the wrong thing to do, but it gives you that value, because essentially what the sort of like average and divide technique does is fit a line through 0. But so no, it's not particularly surprising, I don't think, to me, but it's comforting, because you sort of get the sense that if you go to other galaxies and you're looking on really large scales, then you might not need to really worry about the small scale structure.
Thank you, John. If I could try in the panel Adi and some proclamation.
Yes.
I think galactic astronomers should not offer conflict of astronomy.
Yeah. Oh, that's my opinion 100%. I think. Yeah. Thank you.
Anybody know how to make this thing work? I think you might need it.
If you move it up a little more, still here.
Well, that's not working. Okay, I'll try and speak loudly. Yep.
It was working.
It was it? Okay. Just 1 second. should work. Coming up?
Oh. Okay. That's just a problem up there. They said it's visible up on the screen.
Yeah.
So,
Can you just try and just disconnect and put this back in? I think we can just do the HDMI.
Just plug in again?
Yeah.
Oh, great. Thank you. Okay, I think we're on the road. Thank you. Well, nice to be here. Thanks for inviting me. So this talk is about a phenomenon called the Hercules stream, which it's been known for about probably 30 years, but exactly what's going on here, nobody has quite figured out yet. So big step forward with Hercules, with the Gaia satellite, which, as you know, provides fantastic transverse kinematics and also good radial velocity data. And I'm plotting this is actually a two-dimensional histogram. It's showing the distribution of velocity components relative to, well, they're actually the way I've got it plotted is it's in absolute terms. VR is the in and out radial motion. So a particle that's got no radial motion relative to the sun has got 0. And on this axis, people usually plot the azimuthal velocity, but I've chosen here to plot the angular momentum because angular momentum is actually a good indicator of where stars belong in the galaxy. So a star that's moving around the galaxy in a circular orbit with a local standard of rest has got an angular momentum close to 2,000 units. These are kilometers a second, kiloparsecs, and it's got a radial velocity relative a radial component that's pretty much 0. So these are all the stars that are moving pretty much with the solar neighborhood. But then there's this low angular momentum component which is called Hercules. And for a long time people thought that this was a moving group of stars, maybe the debris of a star cluster. But then when the chemistry was studied and the stellar population, it turned out to be an inhomogeneous collection of disk stars. It's not the debris of a star cluster. It's some sort of bunch of disk stars that have different abundances, different ages. So the stars have ages from about 6 to 10 gigayears, abundances that really range over the whole abundance range that you find in the thin disk. And the inhomogeneity of it suggested that it might be associated with one of the bar-related galactic resonances, like the outer Lindblad resonance. To make that work, you need the bar rotating rapidly, which people thought it was at that time, and that puts the outer resonance near the sun. And it's just a resonance between properties of orbits in the disk of the star and in the disk of the galaxy and the bar. But gradually, improvements have occurred in our understanding of the structure of the galaxy. Now the rotation rate of the sun is believed to be pretty high. Well, that comes from Mark Reed's work. We know the radius of the solar orbit pretty well. We know that the bar is actually quite a long thing. There's this bar in the middle of it. It has a pretty slow pattern speed. So this outer Lindblad resonance explanation doesn't work. It puts the co-rotation where the bar looks as if it's stationary, puts it out about 7 kiloparsecs. And with these parameters, associating with Hercules with co-rotation may be more plausible. And it may be that Hercules is actually stars from the inner galaxy, these low angular momentum stars, trapped around the co-rotation. I'll show you what all that means now. But here's an N-body run which wasn't really focused on the Hercules problem. It just sort of came out for free. These three panels just show you different kinds of orbits that are getting hung up in the neutral points, and I'll show you what those are in just a second. The bar generates just by its asymmetry, and this one here shows you a diagram very similar to the one I started with. It shows you the azimuthal velocity, not angular momentum, in and out velocity. Here's all the stars moving with the sun, and you can see the Hercules stars at rather low angular momentum. So they're being transported out into the solar neighborhood from these kind of trapping orbits. So this is something I'm quite interested in. I worked on this kind of trapping a long time ago in a different context. I was interested to try and understand how bar trapping works, and it turns out to be quite a spectacular thing. Elena Dongia, who I think you all know, has made N-body and hydro models of the Milky Way assembling itself, matching quite nicely to the galactic parameters. And her model grows a bar, and it also shows this sort of Hercules-like feature from stars trapped near co-rotation, but they got enough energy to come out near the sun. So in her models, before the bar formed, the Hercules stars were distributed around the disk. They had the right energy and angular momentum to be captured around these neutral points that appeared when the bar forms. Okay, so this is what the potential of a rotating bar looks like when you get into the rotating frame. So these are just the XY coordinates. The bar is sitting about here. The L4 and L5 neutral points are the ones that are of interest to us. There are another two neutral points out at the ends of the bar that are called L2 and L3. They're always unstable, so they're not potential trapping sites. These ones may or may not be stable, and in the case of a galactic situation, they do appear to be, and they are potential trapping sites. So what happens, as the bar's rotating, stars in the disk get hung up around these neutral points, and you'll see in just a moment they can come way out to the sun, and the sun would be out at about this sort of radius here. Okay, moving along. So what I did, I just took a potential model, and then I integrated up a whole bunch of orbits and studied their stability just numerically. So the potential model is pretty conventional. It's a bar with a semi-major axis of about 5 kiloparsecs, a mass of about 2 by 10 to the 10 solar masses, and then it's got a disk with a logarithmic potential that just gives you a flat rotation curve. This combination, here's the rotation curve due to the bar alone. You see abrupt change at the end of the bar. Here's the total. That's a rotation curve, looks very much like the standard rotation curves we have. Puts the co-rotation at about 7 kiloparsecs. So it's about as close as I could get to a galactic potential. Now, here's the bar again, and it's rotating around in this direction. I'm just studying the trap points around this particular neutral point. And the first thing I did was what you usually do in this kind of study. I just found all the periodic orbits that are hung up around the neutral point, and all of these orbits I test for linear stability to small perturbations. All of these orbits, going right from here, almost to the bar itself, all of these are stable to small perturbations. And they all have pretty much the same period. It's about 4.4 divided by the angular velocity of the bar. And these are really just, they're basically epicycles. If you've sort of met epicycles in your graduate school. So the angular momentum of these orbits that we're looking at, because we're not in an axisymmetric potential, the angular momentum varies by about 10% around the orbit. But the mean angular momentum is pretty much the angular momentum of the neutral point itself, so something just sitting at the neutral point. So those are relatively low angular momentum, and they're the sign that these stars that are trapped around here have about the right angular momentum to be associated with Hercules. So although we've got a situation where energy and angular momentum aren't conserved because you've got this changing potential and it's not axisymmetric, there is an integral, and it's called the Jacobi integral, and it just happens to be the energy minus the angular velocity of the bar times the angular momentum. That is constant. We'll come back to that in just a second. Now, I showed you all these orbits that are stable to small perturbations. It turns out that all of these are also stable to quite large perturbations, so you can give them a very substantial shove, and that greatly increases the effectiveness of this kind of trapping. So this shows you one of these periodic orbits, the red one, and I've just given this orbit pushes of increasing size just to see if I could make it be not trapped, just to deviate from being a trapped. But this entire blue region, this enormous blue region, is all the orbits, what we call quasi-periodic orbits, that are oscillating around this periodic orbit. You see that they cover an enormous region. I've run this for 500 periods, which is pretty much a Hubble time, and even this orbit, it's still trapped around L4. So perturbing the red orbit even more than what I've done here, that leads to an untrapped orbit that finishes up going right around the bar structure. So what's the origin of this huge extended region of quasi-periodic orbits? Because that's really going to make this whole story work. So here's the sun, this little star, and you can see that the trapped orbits in this fairly realistic galactic potential model, these trapped orbits come way out past the sun, so there's no problem in getting them out. So why is this orbit stable region so large? Well, it's because there's a second family of rather slow periodic orbits. And I won't go into these in too much detail, but here's our potential field again. And this red thing, this is the largest member of this very slow family of orbits. These have a period which is about 10 times longer than the fast family of periodic orbits we were studying. And this orbit moves very slowly around this potential hill. This is the forces in here go inwards, so that's a hill, and then they go outwards because it's a centrifugal force. And the huge quasi-periodic orbits are a combination of these two periodic orbits, a bit like epicycles. So we can think of the slow orbit that's just going around this hill carrying with it these faster periodic orbits. And that's really how this sort of trapping works. So with the adopted parameters, the trapping region extends well beyond the solar neighbourhood, consistent with the Hercules stars being trapped around the co-rotation region. So all of these stable periodic orbits have similar extended quasi-periodic orbits around them. I'm just showing you one of them, but they all reach far out beyond the periodic orbit itself and far out beyond the sun. So that's almost the whole story to this point. The next step in this is to try and work out what kinds of stars actually got trapped in this process as the bar structure started to appear. The bars believed to have formed from the disk through disk instabilities over a few giga-years long ago. So which early disk stars get trapped? So what I will do is just run the bar formation process backwards. I'll start with the trapped orbits that we've just been looking at. I'll make the bar axisymmetric by gradually removing the asymmetry, keeping the rotation curve similar. Our Jacobi integral, which is just the sum of the two axisymmetric integrals, that Jacobi integral gradually turns from one integral into two integrals. These two things themselves become integrals, and the goal is to see what part of the early inner disk are we looking at when we study the Hercules group stars. What kind of stars have been brought into the solar neighbourhood by this trapping? What are the orbital properties in the early axisymmetric galaxies that lead to stars being trapped in stable orbits around the L4, L5 points? And I'll probably do this in terms of epicyclic amplitudes and phases in the axisymmetric state. So that's stuff I'm going to do in the very near future. Okay, thank you.
So I realize now in the solar neighborhood, we'll see a glimpse of this through the Hercules moving group. Will it be possible by the end of the Gaia mission to map out the full structure of this, these stars?
No, I mean, we can get really good data out to about a few kiloparsecs. But after that, even when we look at the data we've got now, we can see when we're getting out a few kiloparsecs, it all starts to go a bit fuzzy. So we can study the solar neighbourhood very well, but it gets worse as you go further out.
Maybe you just answered this question, but the L4 and L5 are associated with one-to-one co-rotation resonances. So is it possible that you could find structures associated with other co-rotation
Yeah, I don't think they'll be nearly as powerful because this is such a feature. You've got this very large, the potential at the L4, L5 points, and at the L2, L3, the unstable ones, the potential is almost the same. Very, very gentle falling down. So you've got this huge region. Co-rotation is not just a circle. It's effectively quite a large patch, and this is why all this stuff works. Yeah, I think when you go to higher order things, it won't be quite as spectacular. Yeah.
So is this trapping process a one-way street, or are the stars also leaking out?
You'd have to do something to them to make them leak. You'd have to bump them with interactions with molecular clouds or mergers or something. If you just leave the galaxy in peace, they won't leak. They're very, very stable.
Can't start yet.
You want to use this thing? You've got a quiet voice or a loud voice?
Okay, thank you. Okay, so I'm not very familiar with 10-minute talks, so I'm going to try to do a little bit too much. Can you hear me without this thing? Yeah. Okay. So. Okay. All right, too bad. Okay, so I'm going to start off by just telling you, just very briefly reviewing what this problem is, since I heard that you heard about it last week. So I'll tell you that. But there's really two parts to the talk. One is how to implement a possible solution, and the other is sort of how well it's going to match. So let me just begin. And okay, so what is the Hubble tension, and why should we worry? And so I know there's a lot of observers here. There's a lot of astronomers. We're particle physicists. We like looking for new phenomena. We like deviations. But it doesn't mean we believe all the solutions. But there's a really right now the deviations between the local Hubble measurements and the ones from the CMB is significant. And it's only gotten better in terms of us, worse in terms of you, with time. So we care. And one sign that something is real is that it survives. Now, I know there are possible systematics. I know you've heard about one set of systematics last week that actually puts the value to a value that we actually prefer, so we're not unhappy about that. But the reason you might be dubious that it is new physics is that it is actually really challenging to resolve in theories that you expect to find. So it's worth knowing what are the potentials that can actually make things really work. Okay, and then after that we can test for them, evaluate them, etc. So this really should be an hour talk. So I'm going to try to give you the essential ideas. Okay, so the CMB is sensitive to H0 through the well-measured angular scale, the ratio of two quantities, one of which depends on the Hubble parameter at times before CMB is established, and one which depends on what the Hubble parameter is afterward. Okay, and what's interesting is that it's described as a discrepancy in the Hubble parameter H0, but really it's probably a discrepancy given putting it together with all the other data, including Pantheon, including BAO. It looks more like it's a discrepancy in R sub S. So the sound horizon and the sound horizon at decoupling. Okay, so that looks like it's the thing that's more like, and there's work that other people have done that are listed there that show why it's hard to make it work if you just modify things at what I'm calling late time after CMB is established. Okay, so what it looks like you want is some initial injection of energy that can increase H at early times. And this is from an older paper that just shows you what was allowed at that time in terms of energy injection. And the point is that you can actually inject energy right around matter radiation equality, but if it survives too long before or after, or if it was there for, it probably will be ruled out. Okay, so it's a funny type of injection that you don't usually see. Okay, and they think the key thing to notice is that to get a 10% agreement, to reconcile a 10% disagreement, you're going to need a significant energy injection of order 10%, but it also has to go away very quickly. Okay, so what we wanted to do is find a potential that can really do that. That's of course nice just from the point of view of saying what kind of physics it is, but it's also important to have an explicit potential, because without that you can't really see whether it works. It's easy enough to do the background energy density, but to do the details of the fluctuations that contribute to the CMB, you really want to have an explicit model, or else you just can't do that right. And some of you might be familiar with older work, and you can ask me about in a question session, and I can tell you some of the issues we have. Okay, not from us, from other people. Okay, so what do you need to get this to work? Just in a nutshell, you want the scale which defines the scale over which the energy density of your new field, which I'm calling phi, changes with time, and the ratio of that to the baryons. It has to transition from negative to positive, because you want something that peaks. Okay, so that's of course already looking a little odder, but it's not so hard to do, because you could start off with W phi is just -1, which is to say start off with your field frozen and then have it roll down. And as long as W phi is greater than WB, where WB is the background W, then it will have the desired property and you'll get rid of it. Of course, you have to get rid of it quickly enough, but this is a minimal thing. And again, notice here I'm assuming some sort of constant W. Okay. Okay, and so this isn't what you would get for those of you familiar with axions. It's not what you usually get. You usually get for axions just W phi is 0, and it's not what we want. Okay, so we're not just interested in just some scalar field you might be familiar with. Again, we have 10 minutes, so goodbye. Okay, so what we looked for, and the reason for the title of this thing, we called it rock and roll. The rock refers to oscillations. The roll refers to rolling. Okay. And we wanted to distinguish it from something which is just oscillating, which people had looked at before. So we actually looked for solutions that we could really have control over. And one of the reasons it's nice to have rolling as opposed to very oscillating, wildly solutions is you can actually track them. And as I'll argue also, these are somewhat nicer in terms of they might work. Although sort of rolling solution works too. But if you just say you want something that will be under control so that it asymptotes to a constant W solution, you're led to a very simple class of potentials, which is basically a power law. Okay, so we have V of phi is phi to the 2n, and then n is related to W phi. So WB will be fixed in general, because as we'll see, we basically are going to have this energy peak at essentially matter radiation equality. So basically, we're going to be studying it mostly in a matter-dominated background, what it does, because we'll have it frozen until then. But we did do it more explicitly, but you can understand what's going on just by taking WB equals 0. Okay? So then you can ask, how do I categorize? Well, this is actually a well-known class of potentials, and it has actually been categorized. And you find for low n that you have just oscillating, but that's n less than 2, which is to say phi squared. For 3 greater than or equal to n greater than 2, you could have either a rolling or a rocking solution, what we're calling a rocking solution, which is to say oscillating. And for n greater than 3, you have only the rolling solutions, only the non-oscillating solutions, okay? So I'll show you some pictures to show what's going on, because it's quite nice. So here we're comparing n equals 2 and n equals 5. And you see the n equals 2 curve, and what we have are 2 different possibilities for W, one of which I told you and one of which I didn't really. So one of them would correspond to if you have an oscillating thing and just average, and you can ask for the average W for the oscillating guy what W is, and the other one is the one I just told you, which is related to n explicitly. So this tells you whether the solution you're looking at is oscillating or rolling, and we just can trace it, and you see that. So you see that the cycle average one is working on n equals 2, but the n equals 5 is clearly rolling. Another interesting thing, we had originally started a class of tracking potentials, which are exponential potentials, They just don't fall off as quickly. But you can see that it's actually, it's the limit of the class of potentials we were talking about, which were just power law. Okay. And this also just shows what I just said. So you see for n equals 2, you really do have some sort of oscillating solution. But for n equals 5, it's just it very quickly asymptotes to just rolling. Okay. So what do the energy injection profiles look like? Well, this is actually quite interesting. So n equals 2, I said it's oscillating, but actually it doesn't go right onto the W that corresponds to oscillating right away. It actually looks like it's kinetic energy dominated for a bit, drops off, and then does its oscillation thing, and it will asymptote. Okay, so it's important to keep in mind that first peak, because this is what I was saying before about you have to really track the energy. Because if you just assumed that it was just oscillating, you would get the wrong energy. Here, you actually lose energy more quickly than you would have thought if it just stayed along that W curve. Okay, so and you see that it's we like the rolling solutions, but and they work decently. But you see, the n equals 2 allows you to inject more energy. Okay, so this was done really trying to get your best fit to all the parameters, and this is. And I should say that this was work I did with Pratik Agrawal, David Pinner, who's there, and Francis Jan Siracine, who I don't think is here right now. And all this work was done with them, which was on the first slide. Okay, so you see that, go away. Okay, so you see that the energy density for n equals 2 can be fairly significant, the other's a little bit less so. So the result is that you actually can do better in terms of matching the Hubble parameter. And so again, it's primarily shoes that's driving you to larger value, but here we see that what you get if you're playing VAO plus Pantheon, and you see where the shoes value is with respect to that. So you see that you really do want to get a higher value, and our n equals 2 model does actually get you to higher values. It doesn't get you quite as high as you want, though, notice, so if it really turns out to survive and be that value, it probably isn't this or any other model. And the red curve there is n effective, which is just adding extra degrees of freedom, which is one model you might have seen to try to reconcile these two. And you see we do a bit better. We don't do it as much better as we might have hoped, but we do better. And this is a comparison for n equals 2, n effective, and lambda CDM. And since I'm kind of out of time, I'm not going to have time to go through the details. But what I just want to point out is that the energy injection is our F. It's our energy fraction that we ingest, F5. That directly feeds into RS. If RS is bigger, it directly allows for a larger H naught. But one thing to keep in mind, though, is that our sigma 8 does turn out to be off, because to make everything else work, we do get a sigma 8 that's slightly off. Okay. And this just compares n equals 2, 3, and 4. And so basically all power laws can help you. They all have this nice property that you inject energy at matter radiation. You get rid of it basically by the decoupling time. But that limits the amount of energy you can inject, which limits the amount that you can reconcile it with H naught. And I mean, one thing we definitely learned in this is that cosmology is very constrained already. So, one of the reasons to do this kind of thing is to see how much we can possibly learn from new measurements and how we're going to go about learning it. Because if we know everything already, that of course would be very boring. So we're hoping that there's some room for new physics, and there is some room, but it is definitely a little bit odd. Okay. So to conclude, clearly it could just be systematics and it can all go away. But it's important to ask the question, what kind of new physics can do these things? I mean, what are we learning about late-time physics by looking at this? Like, are things already so constrained that so little can happen, it just isn't even worth looking for? And so we find that you can have a fairly significant injection of energy, but it really does have to be about matter radiation equality. So it's going to be important to see how the measurements of H evolve, of course, and there's going to be all sorts of different measurements, which I'm pretty excited about. But I just want to also mention that there are other ways to study. If once you have a particular model, there are other ways to study the model. Obviously, BAO will be important as there's more BAO measurements at different Z's. That's very important, and as they get better. Large-scale structure might be important, although I don't know how that's going to work. Sigma 8 definitely is worse for us. It's weird because although we have bigger rho m, we have less omega m, so it really has to do with trying to adjust everything to get the high L modes of the CMB to work. and it'll be interesting to look at just structure in general. So ultimately, we do want to know, what the energy density of the universe is. Are there interesting features? So, and this is how you study it. Okay, thanks. No, down.
How sensitive is this to future measurements of the CMB damping scale? I mean, you really,
Yeah.
they're hoping that they can improve those measurements of effective. I mean, if you phrase them from ineffective, the error bars will go down by a factor of 10 in the next.
Yeah. So it's obviously very sensitive to that, but I think it will be in common. I mean, I don't know for sure, but it will probably be in combination with other things because, as you can see, you can adjust A sub s and N sub s a little bit to try to make things match. But if you do that, then you're going to mess up sigma 8 even worse. So it's very, obviously that is what's putting a big constraint on us, is trying to get this energy injection profile narrow enough that it can be consistent with these higher modes. But I think we will learn something from that. David, you have something to say to that?
Let me just point out that I think the feature improvements from ineffective are mostly coming from polarization effects. Ineffective feeds into the polarization spectrum significantly more than the scalar field energy density.
Yeah, that's a good point.
So you're not going to constrain this scenario as much.
Yeah, if you just do it through polarization, then it won't. That's a good point.
So I want to be a little bit of a strange question, because how much room is there in physical cosmology that in lots of other limitations you could that haven't showed up yet?
Yeah, so this is something we were talking about, because we were saying, okay, so the one thing none of us really particularly like about the model is that you really have to get that energy injection right at matter radiation equality to get this all to work. But if you think about it, you can have energy injection all throughout the universe. It's just, this is the time we've measured things really well. You could probably even get away with doing things at somewhat later times. So, but if you put in 10% energy injection anywhere before, CMB time, maybe you have to worry about Big Bang nucleosynthesis, but you can basically have lots of room. It's really in this late time region that things are getting super constrained. So it's hard to answer that in general. So basically so one thing is, these papers said that BAO rules out late time stuff. But, we found you could almost get away with late time stuff if you didn't put in Pantheon. So, but once you put that in, once you put it all together, then you're really beginning to map H of Z at late time, then you are getting very constrained. So, but I think, but in terms of things like, can you find deviations from W? You still can, and you can still probably accommodate the late time stuff, but it would be different kind of potential. But I'm not necessarily motivated.
What are the other implications of the standard?
Sorry, there's one more question. Sorry, 1 second.
What is the other implications of the standard 5 points potential, and does it go together with the early back as well?
I'm sorry. What do you mean by the other stand?
Of the 5 points model.
You mean? I don't know which other implications you're referring to. This is a new field. It doesn't do very much other than add. As far as what we see, it's just adding energy density to the universe. It's not interacting with us in any way other than gravitationally. As far as so that's the thing. It's actually very safe. There's just some energy density that was sitting there that was frozen for a while and then turns on. And so the question is, how can you do it in a way that does affect measurable things but doesn't? So there's not that many other implications as far as we know, other than cosmology. Okay. Sorry, I forgot I had this down still. Well.
All right, thank you. I'd like to tell you a bit about some work that I've been doing here at the CFA for the last little while. And I'd especially like to highlight the last 2 names here, who are actually high school students that Aura Grauer brought in as part of this student research mentoring program. And so twice a week for 2 hours a day, they come in and we sit down and we've been working with this with them in that time. And so it's an interesting project, and I hope this captures some of the excitement. And so this is basically an idea to use something called the VLA Sky Survey, which is an ongoing sky north of Deck -40 survey in 3 separate epochs, down to a somewhat lower depth than previous radio surveys. And so it's at roughly 3 gigahertz, relatively high angular resolution, and it's really nice to compare it with previous surveys, such as the well-known NVSS survey, which was at a lower frequency but with worse resolution with the same sky coverage, and the first survey with similar resolution and sensitivity, but with much smaller sky coverage and slightly lower frequency. And so what we did in this project is to search for interesting changing sources between the VLA Sky Survey, the VLAS, and the first survey, matching angular resolutions. And really the thing was to see what we find and try and figure out what they are. And so I don't need to convince you now that radio observations of extragalactic objects are interesting. As a person who often looks at centimeter wavelength radio observations, we didn't used to claim millimeter observations until yesterday as radio, but now we do. Anyways, so the radio sky is full of promise for finding all sorts of interesting variable objects. I highlight here a plot of various simulated light curves by Metzger et al. And Ido Berger, showing things like on-axis tidal disruption events. I'm just going to swap this out. I think this is it's dying a little bit. Yeah, on-axis tidal disruption events, the afterglows of long gamma ray bursts, and even famously the afterglow of a binary neutron star merger from a couple of years ago. The problem is that all these transients, if you notice the time scale over here on the x-axis, these things are slow, and they're also quite faint. This particular plot shows flux densities in millijanskis. Keep in mind, sensitivities are of order millijanskis at redshift of roughly a half. And in particular, when people actually try and go out and find these things in dedicated surveys with various cadences, that, of course, they find a bunch of variable sources on timescales of a week, a month, and years, with various modulation indices, and there are all these sources up there in red. None of them are interesting because they're all AGN, and apologies to the people who study AGN in the room, but we're looking for other sources here. And so what we did is to take a slightly different approach that's really been motivated by the approaches taken by Greg Halleman and his group at Caltech. And so what we did is to simply first, cross-match FIRST and the VLA Sky Survey, and we're looking in particular in the search at sources that were bright in the first survey, which was taken roughly between 1995 and about 2001, and sources that are not detected in the VLAS survey. And so we set some constraints such that if a source matched those thresholds, it would have to have a pretty steep spectrum of nu squared or steeper. And then we also did a crucial thing of selecting sources with SDSS galaxies at redshifts less than 0.1. So nearby object as well, really to get us a sample of things we might actually have a chance of figuring out what's going on. And so this is what we found. And this is in about 6,000 square degrees of the sky. It's a pretty large survey, and somewhat larger than any previous search for radio transients in the sky. And so we found a bunch of interesting things. While you stare at this, I'll highlight a few particularly interesting objects. So if you look at this one over there, the second from the left on the top, you'll notice that these are two roughly few times 10 to the 8th solar mass galaxies, which are forming stars quite rapidly, where there's a really nice, bright transient offset from both the centers of these galaxies. I'll also highlight, let's say, this one over here, the second one on the bottom, where this one's about 10 millijansky in the first survey and undetected at the roughly half a millijansky level in the VLAS survey, so it's quite bright in the past and faint. And I'll come back to this one much more in this talk. And then there's this final one, which was 21 millijansky in the past and non-existent now. And in particular, its host galaxy, and keep in mind these are all redshift less than 0.1, the redshifts are given, and the angular scales of the image is the same. It's a really, really small galaxy, right? What's a radio source doing in such a small galaxy, you might wonder? And I'll also highlight one thing here. Although some of these are Cepheid-2 nuclei, previous studies of radio variability in Cepheid-2s have only ever found variability of about 30% or less, generally 10% or less. So coming back to this last source here, the most interesting one. So when we found this, we sort of went through a couple of hundred candidates by eye and found this one in particular. We were all quite excited until I remembered that it was actually published last year, and it was the first paper from the VLAS survey, the first and only paper, I stress. And so it was actually published late last year by Casey Law et al., where they claimed this as the first detection of an orphan GRB afterglow. The idea being that, well, and likely off-axis as well in this particular case. The idea being that there was a GRB that went off in this very low-mass galaxy, which is quite typical of long gamma ray bursts, and they fit some sort of a very loosely constrained model for an expanding synchrotron nebula, where at some point the jet sort of starts to come into view as well, and you get a little late time bump. And yeah, it's a very intriguing transient. The actual motivation for this thing was to try and look for objects that look like the host galaxy of the first repeating fast radio burst. And that's an alternative hypothesis for this source, because the host galaxy is similar, the radio source is similar, so on and so forth. And so it's a fascinating source, unfortunately already published for us. But the other source I'd like to just quickly say a bit about is this one over here, which was 10 millijansky in the past, non-existent now, and sitting in this sort of Cepheid-2 nucleus. And what's particularly nice about it is that it was associated with a 50 millijansky source in 1990, obtained through a survey with the Green Bank 300-foot telescope, which fell down soon after. I don't know if you've ever seen a picture of this 300-foot telescope that just literally collapsed on itself. Anyways, before it did that, it did a large sky survey at 4.8 gigahertz and detected this thing, and was really nice because it was also identified by a survey called CLASS, which looked for lenses, gravitational lenses with the VLA, by selecting for positive spectrum sources to target with high angular resolution. And they didn't detect it. They had a sample of about 8,000 sources, and this was one of 2 sources they didn't detect in class. And they said, okay, it's spurious, whatever, we didn't detect it, moving on. It's really interesting, though, because it does seem to fade with time. But what's particularly interesting to me is that it was the GB6 detection, the Green Bank detection, was coincident with the ROSAT all-sky survey, right? But it wasn't detected in ROSAT. So what's going on? Now, if this thing was, in fact, an active black hole at the time, you might expect it to fall somewhere on this so-called black hole fundamental plane, which, of course, has quite a large scatter, but is nonetheless interesting because in this particular case, the radio and X-ray luminosities would predict a black hole mass of somewhat greater than 5 times 10 to the 9 solar masses. But the total V-band luminosity of this galaxy would suggest a black hole mass of less than 10 to the 8 solar masses. And again, when I say the total V-band luminosity, I'm not decomposing the bulge in the disk, which would lower that even more, for example. And so what's going on? We're a bit confused. One possible explanation is that the black hole fundamental plane is uncertain, and if you take a subsample of low accretion rate sources, you might end up with a slightly different normalization, add in some relativistic boosting if there was a jet pointed at us, and it might sort of get you consistent. But the other interpretation that we're investigating is whether this thing was in fact not a jet, but again, an expanding synchrotron source. where if we make the assumption that it was optically thick in 1990, we end up with a reasonably high minimum energy of a few times 10 to the 50 ergs in the synchrotron source. Sorry, 10 to the 49 ergs in the synchrotron source. And a synchrotron cooling timescale of something like of order 20 years. I mean, that's an upper limit, of course, because there are several other mechanisms that can cool a synchrotron source. But it's kind of interesting to compare that time with the evolution time of the source and consider what other mechanisms you need to make a bright synchrotron source in 1990 disappear so fast. We can model this thing with a pretty nice sort of tidal disruption event like light curve. And this is not meant to be a fit, it's just an illustration that we can model the data. But yeah, it's an interesting object. And just to finish off, we've also been looking at things that are now bright. There are two TDE candidates that we're following up quite well, one which seems to have sort of a nice little bright helium-2 line, and another which sits in an E plus A galaxy, which is quite distinctive of TDEs. And to finish, I think this is a really interesting topic. It has been awesome working with high school students to sort of actually go through and find these things and then go about all the things like BPT diagrams they've made. They've looked at Wise colors. They've looked at optical variability. It's been a lot of fun. But I think this sort of radio-selected searches, first of all for tidal disruption events, can tell us something quite important about the actual fraction of jetted versus non-jetted events by also being sensitive to off-axis jets, and also look at TDEs and obscured nuclei. But of course, we are also interested in AGN. AGN are interesting, and especially those with extreme accretion rate changes where we might be able to say something about the occurrence of radio jets. Thanks. It's actually, so I only focused on this one out of this sample. The others of the sample we're still actually just looking at. We haven't really done a thorough analysis. The AGN that I said were not interesting are those from a separate study where they're just probably variable AGN that are bubbling up and down. These are all significantly more variable than those. That's the difference.
Can you look for variables on a short time scale contemporaneously between 3 epochs?
Absolutely, and that's really why they have 3 epochs, to enable exactly those studies. The epochs are about, I think, 30-ish months apart, 30 to 40 months apart. So, and the first half of the first epoch is just done, the second half is just starting.